Okay, so this is the key sort of theory video for the experimental design experiment, which is sort of will help you sort of design your own purification, so you can actually separate these three compounds using liquid-liquid extraction. You've got to apply this knowledge to design your purification. Okay. So the key background theory, some of which has been covered through other theory videos. So for the iron experiment, solubility, the principles of solubility was covered in that theory video. For how a liquid-liquid extraction experiment works, the theory was covered in the esterification theory video. Okay, so do make sure you are brushed up and aware of the key theory from those videos. What I'm going to cover is an additional piece of theory that you need to think about, which is acid-base theory. This is all about how you manipulate compounds to go into the organic or the aqueous layer, so knowing if you're going to protonate or deprotonate a molecule. Okay, so something which might seem before in the other theory videos is this principle that if you've got a neutral molecule, you can dissolve. The compounds will prefer to dissolve in organic solvents. They'll be poorly soluble in aqueous solvents. But if you've got a functional group that you can deprotonate or protonate and convert molecules into the salt forms, then you change the solubility of those molecules. They then prefer to dissolve in aqueous solvents, and they're poorly soluble in organic solvents as well. And this is the principle you're going to have to use and apply to sort of separate these three molecules. You're going to have to try and work out how you can get them to separate out into organic and aqueous layers, and then separate those layers, so then you've got the compounds in different solutions. Okay, so with acid-base theory then, to know if you're going to be able to protonate or deprotonate a molecule, we have to think about a concept called pKa. Okay, pKa, its definition is that it's called, pKa stands for the acid dissociation constant. Okay, it's a numerical value that you get for functional groups and types of compounds in particular, and we use this as a measure of the strengths of acids and bases. So in this experiment, what you've got to do is you've got to think about the pKa's of the functional groups in the molecules that you're using, and then you've got to think about the pKa's of the solutions you're going to be using, and working out if they're going to be strong or weak enough to actually protonate or deprotonate your molecules, to change them into which layer they go into. Okay, so where does this number pKa comes from? Well, if we think about how a molecule with an acidic functional group can dissociate, so we've got a carboxylic acid here, okay, that acidic proton here can dissociate, and so we get H+, and then we can get the anion of the carboxylic acid, the carboxylate. Okay, and we would also call this, another term we can call this molecule would be the conjugate base form. Okay, so we can have the acidic form of a carboxylic acid where it's got the hydrogen, it's got the proton, or we can think of the conjugate base form where it doesn't have the hydrogen, and that's been removed. Okay, now this process is an equilibrium process. Okay, it's reversible. You can protonate or deprotonate a carboxylic acid readily. Okay, but at a certain pH, you will get an equal amount of both the acid form and the conjugate base form of this carboxylic acid. Okay, and that's down to the strength and the stability of this conjugate base form. So the more stable a negative ion is, the more readily available it gives up its H+. Okay, and that means that you've got a more acidic functional group. Okay, so at pH 5, okay, you have 50% of carboxylic acid and 50% of the conjugate base form. Okay, and at this particular pH, okay, this is where we get our acidic dissociation constant. So this is what the pKa number sort of comes from. Okay, so we get 50% of the acid and 50% of the base. So what we say is that carboxylic acids have a pKa value of 5. And that gives us a relative idea of how acidic or basic that functional group is. So pH 5 is more acidic than neutral pH, pH 7. So we can say we know that carboxylic acids are weakly acidic functional groups. Okay, and we can also think about functional groups getting protonated as well, and their pKa values as well, to think about the strength of that functional group. This time we're taking an amine, okay, and the amine is in the conjugate base form, because what we're doing is we can protonate that amine, and so the protonated form of the amine is the acidic form. Okay, now amines, when they're undergoing this equilibrium, okay, we get a 50% equal amount of acid and conjugate base form at pH 10. So amines have a pKa value of 10. And so, again, we can see that this value is higher than pH 7, neutral pH. So we can say that amines are weakly basic functional groups. Okay, and so in terms of trying to manipulate these molecules then, okay, and getting them to turn into their acidic or their basic forms, okay, this is the basic principle. Okay, if we know the pKa value of these functional groups, and let's say we want the protonated form, okay, we want to have, for example, the carboxylic acid to exist in its neutral acid form, then what we need to make sure we do is, knowing that carboxylic acids have a pKa of 5, okay, we need to make sure that the pH of the aqueous layer that we're using is, this is the wrong way around, sorry,